Welcome to this video. Today we're talking about sharpness-aware minimization for efficiently improving generalization. Before we dive into this paper, just take a moment and press the subscribe button. 90% of the viewers are watching videos but are not subscribing. So let us change this and you would support me. So take a moment, I would be very thankful. Okay, this paper was published in the year 2021 in the ICLR conference, and the reason I chose this paper is because it's, I would say, also interesting in the current domain where we are in. We have a lot of pre-training, and sometimes some parameter configurations are generalized much better than others on the downstream task. And one reason for this can be the flatness of the loss curve. So if you choose a parameter configuration that lies in a region where there's a more flat loss curve, if we change the weights a little, then the model tend to generalize better compared to if you're using a model configuration or parameter configuration where if we change a little the configuration, our loss is very sharp, so it gets high very fast. And the reason for this we can find from another paper. It's called On Large Batch Training for Deep Learning. It's just about why we're doing batch training. So what we can see is we have two minima. So one is a flat minima and the other one is a sharp minima. If we are just looking at the loss, we would say, okay, both trained pretty good maybe, and yeah, we are not seeing any difference between both model, and they have both the same loss value. But one is a flat minima, and what we can see is if we now have a look at our testing function, so the red line says us where is our parameter if we want to minimize the test error, then we can see that a small distribution shift in the flat minima is not making so much difference on the loss. But in the sharp minima, we can see, okay, this parameter configuration has a very high loss on our test data set. And this is one reason why flat minimas tend to generalize better in compared to sharp minimas. And the idea of this paper is, let's find a way to find parameters that our loss curve is more flat. And they call it sharpness-aware minimization, shortly SAM. So this is the idea. Let's understand how they are implementing the idea. And before we see the math, let's just have a look at this example. So they trained a ResNet, one with SGD as an optimizer, so just normal stochastic gradient descent, no other optimizer. And this is how our loss curve looks like. And what we can see is, okay, we found a very sharp minima. If you're just changing a little bit of our parameters, our loss spikes. If we are looking at this loss curve, this one is trained with SAM, and what we can see is, okay, if we go a little bit to the right or left with our parameters, then there's not a so sharp increase, and this is what we want to achieve, and this one generalize, and this one generalize not so well, okay? So let's understand the math behind this in part 2. First of all, we define two data sets or two loss curves on two data sets. One is our LS of D, so our data set, our loss on the whole data set, and then we have a subset of this data set, LS of B. Okay, so the loss of our subset. And what they are saying then is, okay, the loss of our total data set, if we are training with this is smaller or equal than 2. The loss of our subset, but not for our current parameter configuration, we are adding a so-called epsilon, and epsilon is looking for the highest increase in the radius of our current model configuration. So we have our model configuration or our model parameters, and then we're having a radius, and we're looking for weights that increase our loss the most, okay? So this is what we are doing here. We want to maximize this. And then we just adding a regularization term. They are changing it later to the L2 norm, so we don't have to focus on this part of the loss function. So this brings us to the point that we have the loss of our current model or parameter configuration, and then we have a sharpness term, and this one is a sharpness term actually. So we are dividing how much, or we are subtracting how much loss we currently have, and then we take the worst case, and then we have the difference between the worst case and the loss we have with our current parameter configuration. And we want to minimize also the difference between those between this loss. Okay, and this is how we could measure the sharpness. This brings us to a point where we have one minimization and one maximization term. Because first of all, we want to minimize our overall loss function, but our loss function has to maximize at first this one here. Okay, so at first we want to find the parameter that is near to our current parameter but has the worst case loss in this region, and we want to find this epsilon. Okay, so for which epsilon this becomes the this will be maximized, and epsilon is just, for example, the L2 norm. So we say we are making a radius about our current parameter configuration, and the radius is defined by p, and we can have a look at this. We can have a look at all those parameter configurations. So, but we don't want to find epsilon with like a brute force algorithm. We want to find it in a very efficient way, and therefore they use a way to optimize epsilon pretty easily. And the first thing they are doing is the first order Taylor expansion. Okay, we are using a first order Taylor expansion if we have if we want to calculate a point on a function that is very easily to calculate, or is easy to calculate. For example, we can calculate the point for the loss for our current parameter optimization for our current parameters, and then we are taking the gradient, and the gradient says, okay, if I go more to the right or more to the left, will it go up or will it go down? So we can get the slope, and this slope, from this slope we are approximating the real value of the function. Okay, this is the idea. We can see it here. Okay, so we have a pretty basic function, x to the power of 2 plus 6, and we have our is for our parameter is, for example, 1. So for 1 we get 7 as a result, and now we want to approximate the parameter 2. So we don't want to calculate it for 2, but we want to find an approximation of it, and instead of putting 2 into the equation of this formula. And what we can see is we're just taking the value of f of 1, and then we take the distance between our current parameter and the parameter where we want to look at. So this is the step size actually, and then we take the gradient, and this is how a Taylor expansion or Taylor approximation actually works. And they're using it then here. Okay, in this function what we can see is, first of all, we take the normal value for w, so our current parameter configuration, we can calculate the loss, and then we take the gradient, and then we have to find our epsilon, so which epsilon is maximizing this, and the epsilon this maximizing this one here. So we have a vector and we have another vector, and the vector that maximizes this is the vector that gives us the largest dot product. Okay, because if the dot product is high, then both vectors are showing in the same direction, and this is what you want to achieve, because this gradient says us in this direction the loss goes up the most, or goes up, and in the other directions go down. So this is what we get, and we want to find epsilon in a way that we are taking the largest dot product, so that we are just looking in the same direction as our gradient looks like in order to increase the loss. So, and therefore it's just a classical dual norm optimization problem. And a way we can do this if we are choosing the L2 norm is just we are taking the current gradient and we're doing a unit vector out of this. So we just scale it by the L2 norm, and then we have our P, and P is our our radius, so our length. Okay, and it was our step size in this example. Now we found an epsilon that maximizes or gives us the point in the region which maximizes the overall loss. And they are showing here pretty complex formula, or it looks complex. It's not so complex, because if you put q is equal to 2, then you get just this what I wrote here. And the intuition behind this is just find the largest dot product. So now we found our epsilon and we have our w, and now we want to make the update for our parameters, and therefore we have to do the differentiation of our loss. And again, our loss is now the loss of our w plus the worst case loss, or we're taking the worst case loss actually here, the differentiation of the worst case loss, and then we have to do the chain rule, and this brings us at the end to the loss of our worst case loss. So we're looking at the worst case model configuration in this region, and we're taking the derivative of this, and then we have another term, and this term is because epsilon relies also on w. So if we change w, it has an impact on this, and therefore we have to do this if we do the mathematically correct differentiation. Why do I say it in this way? Because they're saying here we drop the second order terms and obtaining our final gradient approximation, because they want to accelerate the computation. Otherwise we have to calculate here the second order derivative, and therefore this becomes more computational costly, and they try to avoid this. And they are also saying, surprisingly, if you're using this second term derivative, it's not getting better, so the performance degrades if you're using this. So if you're not using this, we get much more efficient computation, and also the performance gets better. And therefore the final approximation looks like this. And to understand it a little bit more, let's have a view on this visualization. To understand this visualization, first of all, we have our current parameter configuration called V, and we have the gradient that we would take if we are doing SGD, and this is the gradient. And now we want to find the worst case loss, and we are assuming or doing approximation by using this gradient. Okay, so if we are doing the negative of the gradient, we're changing the sign, it shows us the direction of the minima, and if we are just using the gradient, it says where it goes up. Okay, and we want to find the way where it goes up, and this is why we are using just the gradient as the approximation, or it's called the first order Taylor expansion approximation. And what we can see is, okay, this parameter configuration brings out the worst case loss in this region, or in this circle, and this circle has a radius, or we are looking in the radius of P. And then we are doing the update of the weights by this gradient instead of this this gradient here. Okay, and at the end we are here, and so we are at a more good local minima, and this also achieved that our loss curve gets more flattened. Let's just have at the end a small view on this algorithm. Nothing special. So first of all, we have to compute the epsilon, so find the parameter configuration in the region that gives us the worst case loss, and then we take the gradient at this for this parameter configuration, and then we're doing the update. Okay, so if you want to have a look on the empirical evaluation or on the other results of this paper, I will put the link to this paper into the video description. You can check this out. And if you like this video, I would be very thankful if you just press the like button and also subscribe. And we'll see us in the next paper review.